Hi, everyone. Sorry. Good morning. Welcome to my talk. Thanks for coming. I'm so glad you are here. Can everybody hear me? Too high, too low? So now imagine it's Friday night of this week. The conference is over. You're back at your home, ready to relax, sitting on your favorite couch, and you start Netflix. At least I hope you do. So this is the first screen that you see when you start Netflix. The interesting thing about this screen is it's not universal or static. It's customized to your taste. There are 135 million versions of this screen, one for each of our 135 million customers. But this one is mine, personalized to my taste. I do understand it's just filled with crime shows, but let's not read anything specific into that. Moving on. So please raise your hand if you start watching something, anything, within, say, a minute or two after landing in that screen. Yeah, me neither. That's a very generalized experience. Most of us do spend significant amount of time scrolling, browsing on that screen, trying to pick something to watch. And that behavior is actually relevant to our talk today. Let's say it's 20 minutes later, and you are still on that screen. Happens, right? Has happened to me. Meanwhile, our personalization algorithm are continuously running in cloud. So in those 20 minutes, we could have generated a more personalized, better, fresher recommendation list for you. And if that did happen, the question is, how do we get that list in front of you as soon as it's ready? How do we let our application know that a newer, better recommendation list is ready for it to download in the cloud after the application has started and rendered that screen? Push messaging is a perfect solution for this. Our older application, earlier version, used to poll our servers periodically to see if there are new recommendations available. That kind of worked, but it was both wasteful and not that great delivery latency-wise. What was worst is this two twin goals of server efficiency and UI freshness were in direct contradiction with each other. If you decrease your polling interval to get the freshest possible UI, you're going to put more loads on your server because you're going to poll them frequently. And if you decrease the frequency to give some breathing room to your servers, your UI freshness suffers. Now, with push messaging, our servers just push the new recommendation list to the client whenever it's ready. Just as one data point, we cut down our request to our website cluster by 12% when we moved our in-browser app from polling to push. At more than 2 million requests per second, those 12% add up really fast. So please ignore all push notifications on your mobile for the next 45 minutes because we are going to talk about push messaging. Push notifications are terrible for conference speakers, but background push messages are awesome for applications. By the end of this presentation, you would have a very good idea of what is push, how you can build it, how you can operate it, and what can you do with it. My name is Sushil Aroskar. I'm a software engineer at Netflix Cloud Gateway team. All of the HTTP API traffic that enters our system or our ecosystem passes through our cloud gateway. I have been at Netflix at around 9 years now, worked in 3 different teams, and still somehow I feel like I'm still just browsing the list. The real show is about to start. So let's start with defining what is push and how is it different from the normal request response paradigm that we all know and love. This is actually a motivational poster in my local gym. So that's why I stopped going there. This is surprisingly accurate for our purposes today, the definition. Push is really different in just two ways. A, there is a persistent, always-on, long-lived connection between the client and the server that lasts for the entirety of the client's lifetime. And B, it's the server that initiates the data transfer. Something does really happen on server, and then the server pushes the data to the client instead of client requesting it, which is what we are used to. We build our own push messaging system called Zool Push to send those background push messages to our client from our servers. Zool Push messages are very similar to the push notifications or push messages that you get on your mobile, except they work everywhere across all devices wherever our Netflix application runs. And that includes laptops, TVs, game consoles, Blu-ray DVD players, and mobile. To achieve this cross-platform fit, Zool Push messaging uses open and standard web protocols like WebSockets and server-sent event. The Zool Push server itself is open source too and is available on GitHub today. Zool Push is not a single service. It's, in fact, a complete push messaging infrastructure made up of multiple components. First and foremost, there are Zool Push servers. They sit on the network edge and accept incoming connections from clients. Clients connect to these Zool Push servers using protocols like WebSockets or SSE. And once they open that connection, they hang on to it for their entire lifetime. So these are persistent connections. Now, because there are multiple clients connected to multiple Zool Push servers, we need to keep track of which client is connected to which Zool Push server. And that's the job of Push Registry. On the back end, our push message senders, which are our backend services, need a simple yet robust and high throughput mechanism to send push messages to our client. But our applications don't want to know all these complex details of internal infrastructure. What they ideally want is a single, simple one-liner call that lets them push a message to any client given its ID. Our Zool Push library provides them this simple interface by hiding all these infrastructural details behind a single send message call. Internally, send message call takes this message and drops it into Zool Push message queue. We use message queue to decouple our push message senders from our push message receivers because it makes it easy for us to operate them independently and scale them independently. Also, these push queues act like a buffer. They absorb the sudden spike in incoming messages, and they let us withstand variation in incoming traffic. Finally, message processor is the component that ties all of these components together to do the actual push message delivery. It reads some push message from a message queue. It then looks up. Each push message is addressed to a particular push client, either by customer ID or device ID or a combination of the two. It then looks up that push address in push registry. There are two possibilities here. Either it finds a Zool Push server instance IP mapped to that push address, or it doesn't. If it finds a Zool Push server instance, which means that particular push client is connected to that Zool Push server. In that case, it just directly connects to that Zool Push server and delivers the message to that Zool Push server. That Zool Push server is guaranteed to have an open connection to the push client, and it can send that message down. The port it uses to connect to the push server is available only on 10/24 internal network and is guarded by Amazon security groups for obvious reasons. You don't want anyone to push messages to your clients. Sorry. Second possibility is it doesn't find that client's push address in the registry. It just means that client is not connected or online at that time. So in that case, message processor will drop that push message on the floor. These are best delivery efforts, not the guaranteed delivery. Now that we have seen how all these push components act together, work together, we can dig a little deeper into some of them. Zool Push Server is probably the biggest piece of this whole infrastructure. Our Zool Push cluster in aggregate today handles more than 14 million concurrent connections at its peak, and it's rapidly growing. Zool Push Server is based on our Zool Cloud Gateway, and hence shares its name, Zool. It's an obscure Ghostbusters reference, by the way. Zool Cloud Gateway is the one that fronts all our backend services and act as reverse proxy plus load balancer plus application gateway. It handles millions of requests per second. And it was rewritten recently from ground up to use non-blocking async IO. So it provided a perfect foundation on which to build our massively scalable push server. Which begs the question, why do we need async IO? Why normal IO isn't good enough? Many of you are probably familiar with the term C10K challenge. The term and the challenge was originally coined in 1999, I believe. And it simply states, for web to be scalable and efficient, we have to be able to handle at least 10,000 concurrent connections at the same time on a single server. This, of course, as the time passes, we have long since blown past the initial 10,000 number, but the name kind of stuck. This capability to handle thousands and thousands of open connections on a single server cheaply and efficiently is critical for something like Zool Push Server, which has to handle all these always-on persistent connections, millions of them in aggregate. The traditional way of handling simultaneous connections in a single process would be to spawn a new thread for each incoming connection. And then that thread can do blocking read-write operations on that connection. It makes up for a very simple programming model, but it doesn't scale to meet C10K challenge. Mainly because you would quickly exhaust your server's memory, allocating 10,000 thread stacks for those 10,000 threads. You would also most likely pin your CPU cores down, doing constant context switches between those 10,000 threads, so it doesn't scale. Async IO follows a little different model. It uses operating system provided IO multiplexing primitives like KQ or ePOL or IOCP if you are on Windows to register read and write callbacks for all the open connections using a single thread. Then onwards, any socket or connection that's ready to IO will have its IO read or write callback invoked using the same single thread. So now you don't need thousands and thousands of threads to handle as many connections. There's a flip side. Now your application program gets complicated. Because you are sharing a single thread, you cannot use that thread stack to keep any kind of state, which basically translates you cannot use local variables to keep your state. You have to maintain all the state yourself inside your application program. And the typical way of doing it is some kind of a finite state machine. So it does make your program a little more complicated than a normal threaded program. We use Netty to do async IO in Zool. Netty is this awesome open source Java library that is being used by many, many popular open source projects like Cassandra and Hadoop. So it's quite well tested and battle proven. We're not going to go into the details of Netty programming in this talk because it's a topic unto itself. But this is to give you an abstract from 10,000 feet kind of view of how a typical Netty program structure looks like. Those channel inbound and outbound handlers that you see here are analogous to read and write callbacks that we just discussed. And for example, it's very similar in a sense to how Node.js, for example, handles many, many connections using a single process and node threads. And if you are familiar with Node.js internals, you can think of Netty as libuv counterpart in the JVM world. So this is an overly simplified depiction of how our Zool push server's Netty pipeline looks like. Even after simplification, there are a lot of things going on here, but I just want to draw your attention to really just two things, the two highlighted calls, get push auth handler and get push registration handler. You can override or extend these calls to plug in your own custom auth and custom push registration mechanism inside Zool push server. Besides these calls, everything else that you see here, HTTP server codec, WebSocket server protocol, handler, all of these are off-the-shelf Netty components or parsers, which is great, which means Netty is really doing all of the heavy lifting here. Any client that connects to Zool push server has to first identify and authenticate itself before it can start receiving push messages on that connection. We'll let you customize this authentication to suit your need. You can extend our push auth handler, the base class that we provide, and implement its doAuth method to do your custom authentication. The doAuth method receives the original WebSocket connect request as one of its arguments. So you have full access to all the HTTP headers, cookies, and request bodies, and things like that to do your custom authentication inside that method. As we saw, push registry is the component that keeps track of which push client is connected to which push server. And just as we let you plug in your own custom authentication inside Zool push, we'll let you plug in your data store of your choice as a push registry inside Zool push. The way to do that is to, again, extend our another base class, push registration handler, and implement its doRegister method. Example here, register client method. Example here is using Redis as a backing store for the push registry. So you can use any data store of your liking. Still, it should have some desired characteristics. There is a wish list of the sort to get the best possible result. It should have low read latency. This is because you write the push registration record rarely, comparatively, only once when the client first connects to the push server, but you look it up multiple times. Every time anyone is trying to send a push message to this client. So you should prioritize low read latency over low write latency or write throughput. The data store should also support some sort of record level TTL or automatic record expiry, because Zool push depends on this data store feature to get rid of phantom stale registration records. When the push client cleanly terminates its connection, it does the handshake and says, I'm going away, our Zool push server would take care of deleting its push registration from push registry. But you cannot rely on every single client cleanly terminating its connection every single time. Sometimes clients crash. Sometimes your server may crash. Any of that happening will leave behind inaccurate stale record that we call a phantom registration record inside your push registry. And Zul push relies on TTL, record level TTL, to purge those records automatically. Besides these two critical features, then there are usual suspects for high availability, like sharding, and replication for fault tolerance. Given this wish list, any of these would be a great choice for your push registry. There are probably several more. What we use inside Netflix is Dynamite. It's another open source project from Netflix. It takes Redis and it augments it with high availability features like read-write quorum, automatic sharding, and cross-region replication across AWS regions. We settled on Dynamite for primarily two reasons. It has out-of-box support for cross-AWS region replication, which is critical in our use case. We'll see soon enough why. And being a project developed inside Netflix, it has a top tier 1A support available inside Netflix. There is a central operation team that manages and monitors and backs up all our Dynamite clusters. So it's no-brainer for us to rely on their expertise to operate these clusters. We almost get it for free. Finally, message processing is the component that handles backend message queuing, routing, and delivery on behalf of our push message senders. We use Kafka message queues for our push message queues that separate our senders from our receivers. They decouple them. Most of our backend push message senders take fire and forget approach to message delivery. They are fine with best effort delivery. They put the message in the message queue and they carry on with their life, with their work. Few of them might need to know the final delivery status, whether the message actually reached the client or not. And those can get to that status by either subscribing to Zul push status queue, or they can read it off the Hive table in batch mode, where we log every single push message delivery. Netflix runs in 3 different AWS regions. A backend service trying to send a push message to a particular client generally has no idea where that client may be connected. Our push messaging and routing infrastructure takes care of routing that message to the correct region for our message senders. We use Kafka message queue replication to go across the region and deliver messages across the region. In practice, we have found we can use a single push message queue, partitioned, but single push message queue, to deliver all sorts of push messages with all sorts of priorities and still stay within our delivery latency budget, or SLA. But our design allows you to use different push message queues for different priorities. You would want to do that if you want to guarantee that priority inversion never happens. Priority inversion is when a message of higher priority is made to wait behind a bunch of messages of lower priority because you are using a single message queue to deliver all of them. Having different message queues for different priorities guarantees that this will never happen. Our message processor is built on top of Mantis. Mantis is our internal scalable stream processing engine, similar to Apache Flink. It uses Meso's container management system to run message processors, which makes it very easy for us to spin up new message processor instances quickly if we get more incoming messages. In fact, Mantis actually has out-of-box feature or support to auto-scale number of message processor instances depending upon the backlog in push message queue, depending upon how many messages are waiting. This feature alone makes it very easy for us to meet our delivery latency, SLA, under a wide variety of load and still stay resource efficient. So at this point, I would like to switch gears a little bit and go over some of the operational lessons that we learned when we started operating Joule push cluster in production for the first time at Netflix traffic scale. Till that point, we were mostly used or familiar with operating stateless REST services. And Joule push cluster is a different animal, a little bit different at least. So that required a little TLC, tender love and care, when we started to operate it for the first time. The biggest difference between the normal REST service, which is stateless, and Joule push is those long-lived persistent connections that are maintained by the Joule push server. Those connections make those Joule push servers stateful. Long-length connections are great for clients, right? No argument there, because they increase the client's efficiency dramatically. The client no longer has to break and make connections constantly, like in HTTP world. That's why we all rejoiced when WebSockets were finally widely supported and we could get rid of hacks like Comet and long polling. But the same long-lived connections are a headache from point of view of anybody who's operating a server, mainly because they make that server stateful and they complicate quick deployments and quick rollbacks. Let's take an example. Let's say you are trying to fix some critical, high, urgent bug, and you deployed a new Joule push cluster build with the fix. Meanwhile, your all push clients in the field are still happily connected to your old cluster. These are persistent connections, so they open it once and they hang on to it forever. So they are not going to automatically move to your new cluster just because you deployed it. You'll have to forcefully make them switch to the new cluster by killing your old cluster. But if you do that, they're all going to switch back to the new cluster at almost the exact same time, giving rise to thundering herd. So it's a lose-lose scenario. Thundering herd is when a large number of clients or applications try to connect to the same service at the same exact time. It gives rise to a sudden and large spike in incoming traffic that's orders of magnitude higher than your normal steady-state traffic. It's one of the things that you have to watch out for when you're trying to design a robust, resilient system. We found our way out of this pickle by limiting client's connection lifetime. We auto-close client's connection from server side after some time. And all our clients are coded to reconnect back to our servers whenever they lose a connection. So we'll auto-close the connection from server. The client will reconnect back. And because of the way how round-robin load balancing works, that client would typically land on some other server, which takes care of the root cause of all the issues, a single client being sticky to a single server. Of course, we cannot continuously or frequently break the client connection or auto-close the connection, because then we are smacked back in the HTTP 1.1 world, and we get rid of client efficiency. So we have carefully balanced this trade-off. We have carefully tuned our client's connection lifetime to balance client efficiency that we desire and client stickiness that we are trying to avoid. Empirically, we have found somewhere between 25 to 35 minutes is our sweet spot. So from now onwards, I'm going to assume, or we will discuss in terms of 30 minutes of client connection lifetime, which kind of gives us best of both worlds. Not only we limit our client connections lifetime, we also randomize it slightly between client to client, and for the same client even, whenever it reconnects. So many different clients end up with many different connection lifetime. For example, in this case, it would be somewhere between 28 to 32 minutes, because we will randomize them in plus minus 2 minute boundary. This is necessary to give us some defense against a rare but possible event where some network-wide blip occurs. Let's say your router flips and you didn't have this randomized connection lifetime. So every single client exactly has 30 minutes of connection lifetime. In steady state, all your clients started at different times, so their reconnect timeout and the next reconnect is evenly distributed. Now your router flips for momentarily, so all of those clients are going to lose their connection, and they're going to try to reconnect back. And if it was a momentary disruption, they are all going to reconnect back and be successful around same time, around within 1 or 2 seconds. That's a thundering herd, and that's a different issue. But now we have a bigger issue. This network flip has accidentally synchronized their reconnect life boundaries in perpetuity now. They are going to, from this point onwards, all of your clients are going to drop their connections every 30 minutes and reconnect. So now you have the only thing that's worse than thundering herd, a recurring thundering herd. But if you randomize the connection lifetime every time, you will still have that initial thundering herd, a big spike, but now because everyone is reconnecting at slightly different time, you will get this dampened sinusoidal wave of reconnect peak as the time progresses, because as the time progresses, with every reconnect attempt, their next reconnect is going to drift further and further apart. So it's a really cheap, implementation-wise feature to build in that gives you a really good defense against momentary network disruptions. This is mostly an extra optimization. I know I just said a couple slides ago that we close the connection or auto-close the connection from server side, but that's no longer actually accurate. In our latest version, latest release, we flipped it around such that our server now sends a special message to our client using the same push channel and asks our client to close the connection from its end. I know it sounds like a roundabout way of doing the same thing, but we did that anyway because of the way TCP operates. In TCP, the party that calls close on the socket is the party that ends up in what is called TCP time wait state. It's the last state, TCP state in the TCP flow diagram or state diagram. And that TCP time wait state can consume that socket's file descriptor for up to 2 minutes after the connection is closed, because it has to get those retransmitted segments and everything. Now, since our server is the one that's handling these thousands and thousands of open connections simultaneously, our server's file descriptors are a precious and scarce commodity. By having client close the connections, we conserve, the client goes in time wait state, so we conserve file descriptors on servers. There's a flip side to that optimization, though. Once in a while, you're going to get a badly implemented, bad behaving client that does not honor server's connection close connection message. To handle such clients, we start a timer on server whenever we send this close connection message. And then if the client doesn't comply within a set time limit, then we go ahead and forcefully close it from the server side as a last resort. So with all these tweaks, we took care of the stateful sticky connections problem. And for the next task, we focused our attention on making our server, optimizing our push cluster, basically, making it efficient. Our big epiphany here was most of those push connections were idle most of the times. So even with large number of push connections, our CPU, a server CPU or memory wasn't under any particular load. Encouraged with this insight, we picked a really big Amazon instance type for our push server. We optimized all its TCP kernel parameters. Some of them are, for example, shown here. It's JVM startup options and things like that. And we crammed it with as many connections as possible. And then one fine morning, or not so fine morning, actually, few of those servers crashed in production. And we got a visit from our dear old friend again, the thundering herd. Together, those couple of servers were carrying something like close to 1 million connections. And when they went down, all of them came roaring back. You know you have a problem when just a couple of servers going down in production can start a stampede in your system. So we licked our wounds, we learned from our mistake, and for the second time around, we went with a Goldilocks strategy. Now we knew that you don't want to run your server either too hot or too cold. So we picked a server size or server instance type, Amazon instance type, that was just right for us, size-wise. For Netflix, it happens to be the instance M4 large. It's the Amazon instance type with 2 virtual CPUs and 8 gigs of RAM. And from our squeeze and load testing, we have established that we can support 84,000, up to 84,000 open connections on that small server reliably. And if one or even a couple of such instances were to go down, single multiple of 84,000 reconnects coming back is the size of thundering herd we are comfortable with, given our traffic volume. That's the size of thundering herd we can easily handle. So the real lesson here is you should optimize your push cluster operation from the point of view of total cost, not just the push cluster size. I know it sounds obvious when stated like that, but it wasn't obvious to us initially, mainly because we conflated, I think, efficient cluster operation with lesser number of instances. In reality, you want, or you should prefer cheaper and more number of cheaper instances compared to few big instances, as long as your total cost remains the same. And even if you don't have the similar, like Netflix size traffic and you are not too worried about thundering herd, there's another reason you probably should prefer smaller instances over few big instances, because with smaller instances, you can fit your traffic curve. If you are using auto-scaling policies, you can fit your traffic curve more accurately. At low traffic, smaller instances is like small square fitting your traffic curve, so you get most out of your auto-scaling compared to if you just one server takes 25% of your traffic. Then you can't really increase and decrease your push cluster with auto-scaling policies efficiently. The next problem we had to solve was how to auto-scale our push cluster. We just said a thing about auto-scaling, and we do use auto-scaling heavily in production to minimize our cost. But how do we auto-scale push clusters? Before push, in our REST world, our go-to strategies were either CPU or request per second. Both of these, basically these are the metrics on which we would auto-scale our clusters. Both of these metrics are surprisingly ineffective for push cluster. Because there are persistent connections, there are no requests per second to talk about. It's just once they open the connection. And as we have seen, CPU is really low, even with large number of connections. So how do you auto-scale? Turns out, the only real limiting factor for your push cluster or your push server is number of open connections at the same moment. So it makes perfect sense to scale your push cluster by number of average open connections per server. Thankfully, Amazon makes it really easy to auto-scale your cluster on any arbitrary metric, as long as you can export it as a custom CloudWatch metric, and that's what we did. We export our total number of connections from each server process, and we hook up the average of that to our auto-scaling policies. The last hurdle that we had to cross to get to smooth production operation was to make CLBs, or classic load balancers that Amazon provides, play nice with WebSockets. CLBs do not understand WebSockets, or they cannot proxy WebSockets natively. Whenever a WebSocket client, like web browser, wants to open a WebSocket connection with a server, it sends a special HTTP request called WebSocket upgrade request. If the server understands this request, is going to send a special HTTP response back, which is HTTP status 100 switching protocols. And then the server will take this HTTP connection and upgrade it to a persistent WebSocket connection. Unfortunately, CLBs do not understand this initial WebSocket upgrade request. So they treat it as any other normal HTTP request. So whenever a server sends back that 100 switching protocols response back, CLBs think, OK, so the HTTP request response cycle is over, and they terminate the connection. So you do establish a WebSocket connection, but you cannot have a persistent WebSocket connection through CLBs to your client. We worked around this limitation by making our CLBs, classic load balancers, work as a TCP load balancer. So by default, CLBs run as HTTP load balancers and do load balancing at layer 7. But there is a setting in AWS console that you can enable and put your CLBs in a TCP load balancer mode. And if you do that, they will do load balancing at layer 4, in which they just proxy TCP packets back and forth without trying to understand or pass the higher level protocol, which is HTTP. And since they are not parsing the HTTP anymore, it keeps them from mangling the initial WebSocket upgrade request that they do not understand. The good thing about TCP load balancer or CLBs in TCP load balancer mode is they can still terminate TLS for you. You can still offload your SSL handling, your SSL cert management, et cetera, to a CLB that's running as a TCP load balancer. Not so good thing about WebSockets, not CLBs in particular, but WebSockets in general, is they are particularly vulnerable to CSRF, or a cross-site request forgery. This is because web browsers do not put WebSocket under the same strict single origin policy as they would put, say, an AJAX call. So you can legitimately open a WebSocket to any random domain out there, even if that domain wasn't the document from which the document was downloaded. This means your server now has an extra responsibility to check and verify the origin header to secure your systems from CSRF. Thankfully, Joule Push server already does that for you. The last bit of trouble was how CLBs handle deregistering of old instances from whenever you deregister old instances from it. Whenever we deploy a new build, new push cluster, we deregister our old push instances from our CLBs because we don't want those old instances to get any new traffic. What we ideally want in this case to happen is for CLBs to not give those old instances any new traffic, but let the old connections that are already established on the old instances continue throughout till their natural connection lifetime. But that's not how CLBs operate by default. As soon as you deregister, they are going to kill all the connections, which is, again, the invitation for Thundering Herd. Thankfully, there is a good news there. There's yet another setting in AWS console called connection draining that you can log in and you can set, enable, and set it to high enough timeout value. If you do that, then CLBs will let the old connections to the out-of-traffic old instances go on up to that timeout value. So all you have to do is set that timeout value of the connection draining parameter to a value higher than your maximum connection lifetime, 30 minutes that we saw before. If you do that, then they will automatically disconnect on their own at the end of their connection lifetime and move to the new cluster. So you will get gradual shifting of the traffic instead of abrupt Thundering Herd. Once you make all of these tweaks to your CLBs, they will handle lots and lots of WebSockets happily, no problem. But there is a simpler way. After doing all this, it's like your math teacher shows you long division and then shows you the calculator, right? So Amazon has come up with a newer version of their load balancing infrastructure called application load balancers, which are supposed to understand WebSocket protocols natively. So you don't have to make all these tweaks. They can actually proxy WebSockets. Unfortunately, ALBs came onto scene a little too late for us. By that time, we had already figured out all these tweaks, and we had all these production clusters operating flawlessly behind CLBs. So we continued with them. But if you are trying to get any WebSocket-based deployment today, if you are just trying out today, I'd definitely encourage you to give your first try to ALBs. So let's quickly recap best operational practice for push cluster. You want to recycle your connections periodically to get a hang on the sticky connections problem. You want to randomize each connection's lifetime to have some defense against network-wide outage and thundering herd. You should prefer more number of smaller servers over few big servers, again, for better thundering herd characteristics. If some of the servers were to go down, you should auto-scale on number of open connections and not on CPUs or RPS as you would normally do. And either use a load balancer that understands WebSocket natively, or if you can't, for some reason you're stuck behind CLB or something, use it in TCP mode. Every load balancer out there, Nginx, HAProxy, CLB, has a TCP mode built in general. So now that you have this push cluster in production, it's operating the way you want, what can you do with it? Now that we finally have our push hammer in production, we are seeing a lot of nail at Netflix. Our recent Alexa integration is one such good example. When user says, say, Alexa, play Stranger Things, what happens is the Alexa or a Echo Dot sends the user's spoken command waveform or utterance file to cloud, and the speech recognition actually happens in cloud, in Amazon cloud, using Amazon speech recognition service. So now we have a synthesized playback command that our application understands, but it's in cloud. We need an ultra low latency way to send that command from cloud to the application that's running in that user's living room on that user's TV. Push is a perfect solution here. Our application polling the cloud would clearly not do because the latency characteristics are unacceptable. But with push, you can send that command right away to the client. And that's what we did. Our Alexa integration is built on top of Zulpush. We have even more ambitious plan for our Zulpush messaging capability. One of it is remote telemetry. Let's say we have some device in field which is generating a lot of errors, and we don't know why. We can send a special push message to that device. We can target that device now and ask that device to essentially upload all of its state data, its diagnostic details, its application state to cloud so that we can take a look at it and decide what exactly is bugging that device. But let's say with all this extra data also, we couldn't figure out what's wrong with that device. We can always reach to the last and most favorite tool in every software engineer's toolbox. We can restart the application by sending it another message. Now we can do it remotely. What could go wrong? But if something does go wrong, at least now we can send you a push message saying, we are sorry. So I've been pleading the case for push for last 40 minutes or so. At this point, I have only one last request to make. Pull. All of this that we have discussed so far, all of it is available today on GitHub under Netflix OSS repo in the project Zool. It even comes with a ready-to-go toy sample Zool push server that you can start playing with immediately. So give it a try. Take it for a spin. File bugs. And if you would be so kind, maybe even give us a pull request or two. So in conclusion, push can make you rich, thin, and happy. Thank you.